In this sequence of lectures, we'll look at connecting rows from multiple tables via joins, and we'll examine the concept of keys more closely. Now, first let's talk a bit about keys. We briefly introduced foreign keys in a prior segment and saw that many tables have a primary key, often named ID, that the foreign keys from other tables refer to. Let's look at keys a little more closely. Having a way to uniquely identify one row in a table is critical for linking to it from other tables and to searching for information within the table. Many tables provide this unique identification via one column that gives a unique identifying key, often, though not always, an integer. Bakery 1's customer.id and receipt.id are typical examples. Each row in the customer and receipt tables has a unique ID value. And as we'll see later, one can even configure the table so that the DBMS automatically assigns the next key value in succession to each row added to the table and blocks any modification of a key value that would result in duplicates. In Bakery 1's customer table, for instance, the DBMS might automatically assign the next ID of 21 to a newly added John Smith row, and would prevent, say, altering David Calendar's ID to 5, since that would be the same as Travis Dunlow's key. Keys needn't be integers, though perhaps 90% of them are. Any data type, though, with a sufficient range of values, like a string, may be used. Bakery 1's product.id is a key, but it's a string instead of an int. And importantly, keys needn't be single columns either. Sometimes a row can best be identified by a combination of several of its columns. A table, say, of students from multiple universities might have a university name and a university student ID column. And together those would uniquely identify a student, though the student ID alone might not if two universities had the same ID for different students. A table of tickets might have columns for the date of the ticket and the ticket number. If ticket numbers start over from 1 on each date, the ticket number alone would not suffice, but the combination of ticket number and date uniquely identifies one ticket. Most DBMSs let you designate single columns or combinations of columns as a key, and a DBMS can enforce uniqueness across a multi-column key, though not generally the automatic assignment of key values the way it can for a simple integer key. Now we'll discuss the theoretical meaning of keys later on, but a brief overview is in order here. Defined most broadly, a key is any column or set of columns that uniquely identifies a row, and it has to meet specifically 3 criteria. First, every row has to have values for all the key columns. Second, no 2 rows could ever have the same value for all the key columns. No 2 customers would have or 2 students, would have the same university name and university ID, for instance, no matter what data might go in the table. They might have the same values for some columns. 2 students might have the same ID, or they might have the same university, but as long as the combined values of all the key columns are unique, then that uniquely identifies a row, and condition 2 is met. And the third condition is that no column in the key should be superfluous. You couldn't get the same effect by dropping a column. For instance, if the key for students at universities had a university name, a student ID, and a first name and a last name, the latter 2 columns would be superfluous. The student would have been uniquely identified without including those 2 last columns. Now, with those 3 criteria in mind, let's try a few examples to see which of these qualify as keys per the criteria and which do not. And for those that don't, identify which of the 3 criteria are not met. So here's the list. First and last name for a table of people. Would that be a valid key or not? The UPC, or Universal Product Code, and product name for a table of barcoded products. A driver's license number for a table of people guaranteed to be from the same U.S. state. Red, green, and blue values for a table of colors. Receipt date and customer name for a table of receipts. And credit card number and expiration date for a table of credit cards. So if you've given that a bit of thought, first and last name, pretty obviously not a key. Two people can have the same first and last name, so this fails condition 2. Number B, UPC and product name. Also not a key, this time because product name is redundant. A UPC is completely unique on its own, and we don't need a product name to go with it, so it fails condition 3. Driver's license, again, not a key, and this time because not everybody has one, so condition 1 fails. Red, green, and blue values for a table of colors. This might be a little unfair because you have to be a bit technical to know this, but every color can be uniquely identified by its red, green, and blue combination values, and thus it is a key. Those are necessary, all three of them, and they are sufficient to uniquely identify a color. Number E, the receipt date and customer name for a table of receipts, and it's not a key. Two different receipts might be for the same customer on the same day, so it fails the condition 2. And credit card number and expiration date, same deal, not a key because credit card number alone uniquely identifies the card. Same deal, I should say, as for the UPC. There's a superfluous piece of data here, and so it fails condition 3. Now, if you got most of these right, good. If not, you might spend some time coming up with key examples of your own that are valid and also that fail one or more of the 3 conditions until you're comfortable with the idea. It is, so to speak, a key concept in database design. So now that we understand what a key is, let's look at the additional concept of a primary key. Now, keys are obviously useful for looking up data, but the most common use of a table's key is for other tables to link their rows to its rows via a foreign key. Henceforth, let's abbreviate that F key. A good example is customer ID in the receipt table, which uses the ID of the customer table to identify a row in that table. A single or multi-column key that is used as the target of foreign keys from other tables, like customer's ID, is called a primary key, or PK. All the keys in Bakery 1 are primary keys. Most DBMSs let you designate a key as primary or as non-primary, and the DBMS will enforce uniqueness rules on all keys, but primary keys are implemented more efficiently than any other keys. So looking up a row by its PK is the fastest way to find it. This makes PKs the preferred means of row lookup and the preferred target of foreign keys. And for some database management systems, they're the only permitted target of foreign keys. And since we're talking about PKs and FKs, it's a good time to introduce a type of SQL query that makes use of them. Recall the preview query from an earlier segment listing dates of all receipts for Travis Esposito without using his customer ID explicitly. And this is how that query looked. Now, the from clause in this query lists 2 tables, customer and receipt, separated by commas. Without a where clause, the result of such dual listings is a set of joined rows having all columns from both tables. And there'll be one joined row in the set for every possible pairing of rows from the 2 tables. If the first table has 5 rows and the second has 10, then each of the first table's 5 rows gets paired with each of the second table's 10 rows for a total of 50 pairs. In mathematical terminology, that's a Cartesian product of the 2 tables, to be technically exact. It's probably easiest to show this in practice, so let's try out a simple select here in MySQL. So here's a MySQL session which I just fired up, and I'm using Bakery 1, as you can see. And let's paste that query in there and stand back, because it's going to produce a very large listing. Total of 4,000 rows, as it turns out. And the reason for that is that there are 20 customers and 200 receipts in the database, so a Cartesian product of every customer and receipt combination totals 4,000 rows. Now, if you run it in Workbench, it'll at least cut this off at 1,000 rows. And in MySQL, you can limit the output to a given number X of rows by just adding limit X. I'm going to, whatever the number is, I'll use 100 here and cut this off at 100 rows so we can at least look at it reasonably. I'm going to go into the top of that. Looking at the first several rows, what we can see is that each row has every column from both tables, with customer columns first and followed by receipt columns. And note that receipt 10,013, I guess that is grouped with every customer. And then receipt 11,548 is again combined with every customer. And a little further on down, receipt 11,891 combined again with every customer, and so on. Every combination is represented. And there's no selectivity to this Cartesian product. For instance, it's not grouping receipt rows with the customer rows that they link to. Well, okay, it is, along with every other possible pairing, but not selectively. Such an unconstrained Cartesian product is rarely useful, and in 99.9% of cases, it's trimmed with a where clause that limits the output to combinations for which a foreign key in the row from one table, like the customer ID in receipt, matches the corresponding primary key, like ID, in customer. So in our case, that being receipt.customerID matching customer.ID, let's try. Adding that clause. Thus. Now the result is a lot smaller. Each receipt row is paired with just one customer row. All these are different receipts. If we scroll back up and look, there are about 200 total rows, and each individual receipt is paired with the customer to whom that receipt belongs. Juliet Logan, ID 1, for instance, has 11 receipts, all with customer ID 1, and there are 11 joined rows matching her customer row with each of the 11 receipt rows. Terrell Arzt has 6 receipts, and there are 6 joined rows with him and each of his receipts, and so on. A Cartesian product plus a foreign key equals primary key clause, like this, is a powerful combination. This combination is called a join, and it's not only a common relational operation. In a certain sense, it is the relational operation. Foreign keys and joins are to databases what pointers and dereferences are to programming languages like C. We'll be dealing with them throughout the course. So now that we've narrowed our join query down to rows that make sense, we can make 4 further refinements. First, each joined row still has every column from each table, so let's fix that by selecting purchase date to show just that column. And we can augment the where clause with an additional and to choose only Travis Esposito receipts, like that. And receipt is actually redundant in receipt.customerID because only the receipt table has a customer ID column. So let's remove that qualifier. We need to keep customer.ID because both receipt and customer have an ID field. And then finally, we could add an order by clause, third line here, to sort in a descending order of purchase date. If we do all that, we have arrived at the preview query from the last lecture that we were talking about at the beginning of this segment. And we get Mr. Esposito's purchase date of receipts in descending date order. Now, before we finish up here, let's talk a little bit about the efficient implementation of joins. A Cartesian product happens in principle, and in practice if you omit the foreign key equals primary key clause, but no DBMS worth its salt would actually generate the whole Cartesian product and then filter most of it out via that FK equal PK clause. DBMSs employ a query optimizer, which makes heavy use of relational data theory and figures out how best to carry out the join without generating excess data. In this case, the optimizer would probably go through the receipt table and for each row find the customer row whose ID matches customer ID. This is efficient because primary keys, like customer's ID, are generally indexed. That's something we'll talk about later. And they're much faster to look up than a normal column. As we mentioned, primary keys have that property, quick lookup. The net result is the same as generating the whole Cartesian product and then filtering out only the desired row pairs, only the desired joined rows, but the implementation is a lot faster. Now, in the next lecture segment, we'll go through a series of in-lecture questions involving join queries.